No, that's fine. That's fine. Okay. So we will present the last speaker, Steve Huntsman from BAE System in UK. And his talk is about sampling and statistical physics via symmetry. The floor is yours. Could you hear me? Yes? Ah, il m'entend pas là? Could you hear me?
Yeah, I can. It's hard. It's hard to hear otherwise without the microphone.
Okay, it's up to you.
All right, great. So I'll get started then. So uh, thanks to the organizers for inviting me, and I'm very sorry I can't be enjoying the foothills of Mont Blanc with you all. I'm sure it's quite lovely, but I hope to share some other things that I think are lovely too. So I'll be talking today about sort of two topics that I feel are related. And the first is how to do Markov Chain Monte Carlo via symmetry, and the second is how to really do statistical physics via symmetry. And these are sort of de novo constructions in each case. And what I'm showing in the upper right here is the results of a algorithm that outperforms the state of the art for doing things in parallel. And I'm showing that in dots and the sort of state of the art in a solid colors for various degrees of parallelism. And so we'll get to that about midway through the talk. And what I'm showing in the sort of bottom area is a notion of temperature for a physical system that draws really just from symmetries. And I'll talk a little bit about some sort of physical ideas that might make the application of that interesting. So I'll jump right into the first part. There we are. So Markov Chain Monte Carlo, I'm sure you all know, it builds a distribution, a Markov chain that approximates the distribution in the limit. And the reason is that partition functions are hard to compute. And so you want to build a Markov chain that has the sort of desired invariant measure as a workaround. And once you do that, you get that the expectation value of a function does what it ought to, even though the Markov property implies correlation of successive samples. And the price that you pay is the convergence is slow. So you'd like to have Markov MCMC methods that go faster. The usual way that these algorithms are structured is to decompose them into proposal and acceptance steps. So you propose some new state with some probability, and you accept that with some other probability or stay where you are. And that decomposition implies a particular sort of form for the chain matrix. And so most of the time people are focused on proposals. We're only going to worry about acceptances in this talk. So the typical algorithm, you pick a runtime because it's hard to tell when you've converged, and you build your sort of transition probabilities. You initialize things and you keep proposing, you accept, move on to the next step, and your output is this sequence of states that ought to approximate the product distribution. And so a preeminent example of this is the Hastings algorithm, and I won't belabor it largely because I'm sure everyone in the audience knows it, but the idea is that your acceptance probability has a particular sort of form where you use the structure of the desired invariant distribution and sort of symmetric matrix to enforce what the acceptance probabilities will be. And there are two sort of simple cases. One is when this numerator S is equal to 1, and that yields what's called the Barker sampler. And the other is when you sort of saturate what's possible while maintaining positivity or non-negativity of elements. And that's the Metropolis Hastings sampler that we all know and love. So the idea of Lie groups and Lie algebras might not seem related to that. And I'll just belabor the obvious. A Lie group is a group in a manifold, and there's lots of classical real examples like the orthogonal group or the special orthogonal group, and more exotic ones. We're not going to do representation theory here, but again, as I'm sure you all know, these things have tangent spaces and a Jacobi identity, and the cases that we're concerned with are pretty simple. They're not infinite dimensional, they're not complex, they're just subgroups of real matrices. And so The usual commutator is the one that we use for the Lie algebra, and the matrix exponential does all the things that you would want it to. So once you have a measure of the sort that you want an MCMC algorithm to get, you get a Lie group. And so the starting point for that is the stochastic group, which is just all of the matrices whose rows sum to 1. And here's a basis for it. And here when I do this brackets, I just mean the set from 1 to n. And if I want to take a subgroup of that, I can say, well, this angle brackets p, the subgroup generated by everything that leaves this invariant distribution fixed. And it also has a very simple basis. So I take this ratio of probabilities. I say the last one is sort of special just for convenience. And take that ratio, and it turns out that this is a basis. A couple lines of algebra will suffice to convince you of that. I won't do it here. But I want to sort of highlight this notation with the uppercase or with the superscript p in parentheses. We're going to see that sort of thing a lot throughout the talk. So just recall that if that's there, it's referring to the particular distribution that we're concerned with. So if these probabilities are of the form that we're all familiar with from statistical physics, something divided by a partition function, these ratios don't depend on the partition function. And I believe this is basically why MCMC works. Right? This basis doesn't depend on the partition function. And we're going to build matrices in this Lie algebra and in this Lie group that don't care about that. So we'll dive into a little bit of algebra, and this may be a little bit of a conceptual detour, but bear with me. So if we take some positive integer I and we just take powers of one of these basis elements, we get the same thing times some appropriate scalar. And that's convenient because we can immediately exponentiate. And the particular functional form of this is not important so much as that I want to sort of highlight the thing other than the identity matrix is going to be parameterized by this guy here that I'm writing as f. And in what follows, the sort of diagonal case is going to turn out to be particularly important. And so towards that end, we're going to take, again, a slight detour. We're going to talk about sort of monoids instead of groups per se. So here we're going to look at all the transition matrices that fix the vector of ones and that are non-negative. And we're going to do the same sort of thing for this sort of angle brackets of P. So this is really where we want to live. The things in this object are non-negative. They leave the invariant measure invariant. And so they are sort of candidates for doing MCMC. And just as an aside, you don't have the inclusions that you might seem to. And the reason is that the inverses of these things have negative entries. So again, just to reiterate, this angle bracket P plus is where we want to live. So we're going to start by building a nice element of that. And here's the lemma. If you take some parameters T sub j that are non-negative, and you do this sort of sum of the basis elements weighted like that, then the exponent is in this object. And the proof is really just writing down what these basis vectors look like and recognizing that this is the generator matrix of a continuous time chain. And if we just have a single one of these T sub j's, we get a pretty nice closed form element. That function f that you remember from a few slides ago times this basis vector plus the identity. And we can construct this analytically. There may be some other sorts of things we can do. So for instance, if you take various sorts of possibilities for j, k, and l, and m here, you can get closed forms that they're quite long. In a computer or algebra system, they'll take several pages, but they seem okay. And there's others that have manifestly negative entries, but I'm not sure that actually breaks anything. I haven't had encouraging results playing with that, but it's not clear to me, though it should be, that that would actually break an MCMC algorithm. That said, this simple lemma above is already enough to recover some classical MCMC samplers. So let's see how that works. So the sort of trick that lets you stick to algebra is to say that you're always in the nth state, you're going to apply this matrix that treats that nth state as privileged, and so that sort of transition to a different state is generic. And if, for instance, you take your transition matrix to be the one that we just talked about, you get this for your matrix element from going from n to j, and you could write what that is, in sort of atomic primitives. And if you want to maximize it, it would turn out that you do that at t equals infinity, and what it really is this. You take that ratio, divide it by 1 plus the ratio, and the sort of corresponding matrix turns out to correspond to the Barker sample. And you can do better by saying, well, that doesn't actually lie at the edge of that set angle bracket P plus. So if you say, I want to get to the very boundary of it, then it turns out that you push a little bit further. Instead of taking this f, you'll take some free parameter tau and say, let's go as far as we can until things are on the verge of becoming negative, and that yields the Metropolis sampler. And I'll leave it to you to look at the paper if you want to follow the algebra, but it's not hard. So in this perspective, the Barker sampler works along the sort of motif that we've already seen. You do some initializations, and for every step in the loop, you relabel states so that your current state is the nth one. You make a proposal for some state in everything from 1 to n minus 1, and you accept it with this probability. Then you undo the relabeling and keep going. And the Metropolis sampler is the same thing, but you change this acceptance probability. So what happens if we're willing to try to generalize this, to sacrifice some sparsity? So these are pretty sparse matrices, at least in the Lie algebra setting, and that's really where the simplicity of the MCMC algorithms comes from. So what if we propose multiple states? Now, if we do that, we expect things to go faster, but to be harder, right? So you could take this to an absurd extreme and say, well, if I take the column vector of 1s times the row vector that's my desired measure, well, that's a very good transition matrix for an MCMC algorithm, but it presupposes what you're trying to compute. So you want to go somewhere in between that and the sort of practical starting case that we've already seen. And the sort of key thing to do to interpolate between those extremes is to build more interesting elements of this angle bracket P plus. So we'll do a little bit of algebra towards that end. And again, bear with me notationally. So we'll consolidate these ratios into a vector of ratios. And the minus just means we chop off the last entry. We'll have some proposal set that has D proposals in the set from 1 to n minus 1, right? Every place where we're not currently. And we'll take some matrix in codimension 1 that sort of parameterizes what we want to do. So notationally, when we have this subscript script j, it just means that we're taking a submatrix based on whatever that script j is. And when we add the superscript p, just means that we're doing the Lie algebra vectors with it. And again, this script j here just means that we're taking a subvector. And so the sort of lemma that pops out is that if you multiply a couple of these, then you can pull back the parts without this without these superscripts, like so. And this is really a mess notationally, but the reason for it is that doing the simplest case is a page of very mind-numbing algebra otherwise. So we don't have to internalize it for the talk, but just rest assured that it's sort of important to keep things concise. And with this in mind, we can build a sort of generalized Barker matrix. And so the rationale here is, pick some omega. It's just a parameter that's there for fun mostly. And this construction that we saw from the last slide, we're going to invert it, and we'll use the Sherman-Morrison-Woodbury lemma to sort of write down what that inverse is, and that's where this form comes from. And the reason for doing that is you can exponentiate it nicely. You get this sort of ugly thing. It's not too bad. And the sort of salient point is that it's in the thing that you want it to be. It's in this angle bracket P plus, and it's also invertible. And the sort of fallout is that you can define this sort of Barker matrix that doesn't depend on this free parameter because you've taken it away by construction. And it is a sort of bona fide MCMC transition matrix. So we'll talk later about how good it is. But taking the same sort of principle as before and saying we can push things a little bit further, we can build a Metropolis matrix. And the idea is just instead of on like here where you push things by this sort of analytical amount, you just push forward as far as you can. So you take the biggest entry that keeps you from becoming negative and adjust it accordingly. So you hit the boundary of this angle bracket P plus. That's what I'll call the Metropolis matrix. We can look at some examples. So here's the sort of desired invariant distribution. So n equals 5 and d equals 3. So right now I'm in the 5th state. I want to get to one of the first 3. And so here's that sort of messy A matrix, and I can get these intermediate matrices, and I'll just show you that this sort of intermediate thing changes as I change that omega. But the Barker and Metropolis matrices don't care. And again, since we're in the last state, what we really care about is the bottom row of these. And you'll notice that the sort of off-diagonal entries are the same up to normalization. But the advantage of the Metropolis matrix is that it has a smaller diagonal entry, and so you're more likely to explore the rest of the probability space using it. And so following through the algebra, we can just work out what these things look like in general. And again, we sort of have this idea of relabeling. You don't specify a proposal, and you can work out what the matrix entries are. And when you go through these intermediate steps, the sort of important parts of the Barker sampler are basically as before. I'm writing here sort of I guess it's an inner product. This is a row vector and this is a column vector. And so you're just taking all the ratios and adding them up, plus 1. And if you're moving, the ratio's on top. If you're not moving, 1 is on top. And the Metropolis sampler is sort of the same. There's an added term in the numerator because you've got to get rid of this sort of extra bit of slack that's in there. And when you look at the matrix entries, again, they're very similar, but you've got this little bit of slack that you've removed in the bottom here. So algorithm, once it's implemented, you should be familiar by now. You do your initializations, you relabel states every time, you propose some subset of things, and you're going to pick something in that proposal set with that probability. You undo the relabeling, and you keep going as long as you decided to. And so that apparently is this ensemble MCMC algorithm of Radford-Neal, at least as it's presented in a paper by Martino. And the Metropolis version of this, he changes the matrix, and it's a slight specialization of a waste recycling Metropolis Hastings construction by Delmont and Jourdain about a little over 10 years ago. So let's see how these work. I'll take a Sherrington-Kirkpatrick glass, and we'll sort of use the same random numbers for each run. We'll just do a single run so we can see how things play out. And we'll do, sort of low inverse temperature. These single runs actually tell us something. So what I'm showing here is it's a log-log plot, number of steps of the algorithm, the total variation distance between the ground truth and the empirical distribution. And I'm showing various degrees of parallelism for various sizes of the proposal set. So D equals 1 is just sort of classical MCMC. And here's where we're proposing 2 or 4, or we're proposing 16 other states. And the dots are the sort of higher order Barker sample. So in particular, the D equals 1 case is just the Barker sampler. And the lines are the higher order Metropolis samplers. So again, the red line is just the Metropolis Hastings sampler. And this inset diagram shows, instead of using time steps as the axis, they're sort of normalized by total amount of parallel effort. And so, while this shows that you converge faster by using parallelism, this shows that the parallelism comes at a cost. So I don't think that should be a surprise. So let's change the temperature a little bit. Right here, beta is 0.25. Let's change it to 1. And you'll see that most of the advantage goes away. You can, if you squint really hard, you might be able to see some of the dots as distinct from the lines. But it's mostly concentrated at the sort of non-parallel classical case. With, I think maybe 1 or 2 exceptions buried in there. So not as interesting as we would like. Let's try to do better. So we can say, given some parameter matrix tau, we can do this sort of superscript, subscript stuff that I alluded to before, and subtract it from the identity, and that'll be a transition matrix if some linear constraints are satisfied. So here's what that transition matrix basically looks like, and the sort of details of what these are in the paper, but you can more or less guess from the notation the sort of things that they are. And once you've built this sort of apparatus, you can say, let's pick an optimal value via some linear program. So you've got some generic objective where you've got this matrix in the middle, and that's what you're going to optimize, and you're going to fix x and a y. That's your objective. And there's a sort of natural choice of these that gives a Frobenius norm approximation of this sort of Platonic ideal of 1 times p. And so the details of that are in the paper. There's a lot of sort of tensoring and things like that, and various reformatting of linear programs to get it into a form that you can do in MATLAB easily. But there's nothing particularly deep there. But I'll show you an example. So the same example as before, and the same Barker and Metropolis matrices as before. And when you do this linear program, this is the matrix that results. So again, we actually care about just the last row of this, and you'll notice that it's substantially better from the point of view of being able to explore more of the probability space. Right up to normalization and diagonal entries, everything is the same, but this diagonal entry is much smaller than a 9 or a 10. So it does do better. So to actually translate this into a sampler, it's a little bit more involved than what you've seen before. The same sort of setup, the same labeling and proposal. So you do this sort of linear program at every step. It doesn't have to be big, but it's still a linear program, so it takes some effort. You build your transition matrix, and you do the acceptance. And as far as I know, this algorithm is new. And as far as reviewers know, this algorithm is new. Hopefully it's actually new. And it does better than this higher order Metropolis sampler. So I'm showing the same sort of plot here, but I've flipped what dots and lines are. Now the dots are this sort of higher order programming sampler, and the lines are the Metropolis one. And you can see that the dots are basically below the lines. Not a lot, but some. And again, bear in mind this is a very sort of small example, right? It's a 9-spin Darrington Kirkpatrick class. Let's change the temperature. So if we go to beta equals 1, you can see that there's a substantial difference. This programming sampler clearly outperforms stuff, and it won't always be the case. There'll be fluctuations. See them over here, but the general sort of trend is also, I think, equally clear. And this is a log-log plot, so any difference is a big one. So the argument that I want to leave you with for this part of the talk is that symmetry really does unify MCMC algorithms and produce new ones. This particular sampler might be useful for Bayesian inverse problems, a lot of sort of complicated modeling involving PDE stuff. There are a lot of things I haven't tried, so doing continuous variables, it'd be a lot more technical. You'd have distributions a la Schwartz, or infinite dimensional Lie groups. That's all going to add a lot of complexity. Trying to have a proposal mechanism that is somehow cognizant of the structure of this algorithm. I haven't do that. Doing more general optimizations, convex stuff. Again, haven't looked that, or looking at if this is reversible. So as I mentioned, it's possible to build sort of transition matrices where the nth row is well behaved, but there's negative entries elsewhere. And it's not clear to me that this actually breaks an MC-MC algorithm, right? The sample paths shouldn't really care what happens for those other rows. But as I said, I did some experiments and they weren't encouraging. But I'm not sure why they weren't encouraging. And again, sort of the Platonic ideal would be to say, or maybe a step before the Platonic ideal would be to say, instead of having 1 times p, maybe we could sample vertices of this, but that's computationally intractable. So that's sort of where the frontier is if we're going to pursue these ideas. So I'm going to, from there, segue into a sort of complementary part of the talk, which is using symmetry to derive statistical physics. And that sounds grandiose, and I think you'll find that claims sort of are, but I hope you'll also find them justified. So if we have some data, just statistics of state occupation times, we're going to get an effective inverse temperature. And there's really only one of these that makes any sense if you accept the Gibbs relation and sort of physical notions of scaling. And as you know, once you have a temperature, you get an energy, and this sort of setup is going to suggest things about non-equilibrium steady states, but also data analysis, which is where this thread originally came from. We're going to talk insofar as time permits, and Frederick, please tell me once there's like 5 minutes left, because I'm cognizant of the cocktail hour, and I certainly wouldn't want to stand in between anyone and beverages. But I'll try to talk a little bit about ANOSOF systems and the chaotic hypothesis. I'm going to start by saying, where's the Gibbs distribution come from? So I never felt happy with the derivation in Landau and Lifshitz or in Feynman, and so I tried to do a new one. And I haven't seen this. Maybe it's out there, and if it is, please let me know. But the basic assumption is that the probability of a state only depends on its energy. And so I'm sure many of you or all of you have seen sort of Fatty's characterization of entropy from a few sort of symmetries, and I hope that this sort of follows in the same vein. So energy only depends, or energy is only defined up to a constant, and so there ought to be some function f so that this probability, it gives you the same thing if you add this constant to it. And so if you define this g sub e accordingly, you can sort of cross multiply and find out that, well, this ought to be obviously 1 when epsilon is 0, and this probability takes this form. And so we're going to memorialize that on the next slide. This is what we just saw. And if you, again, do some basic algebra, you'll get that f times this g sub e is f plus epsilon. And so you can take a derivative. And here's what the derivative looks like. You can pop that out. And that implies this functional form for f. So whatever this g sub e is, it plays a sort of central role. And if you say that that's going to be the negative inverse temperature, and without loss of generality, you set c equal to 1, you get the Gibbs distribution. And this argument is self-consistent because of the sort of fact that, once you say that g sub e equals this exponent of beta, then the e subscript sort of disappears. And as long as you're thinking about this in terms of the canonical ensemble, it's fine. So, okay, we came up with the Gibbs distribution, and now we're going to define some sort of auxiliary coordinates. So we're going to have some finite number of states, some invariant distribution, and some characteristic timescale where I'm waving my hands. Can you guys see me waving my hands? Because that's what I'm doing. So think of it as like a mixing time. And so we'll talk in terms of times or characteristic times rather than probabilities sometimes. And you can go back and forth with some elementary algebra, and I'll define this tuple H, which is just these as yet undefined energies and temperature. So what we want is a way to go from T, this set of characteristic times, to this sort of energy coordinates. And in statistical physics, is sort of, you know, the goal is almost always to go from H to P, right? Someone gives you the energies and the temperature, you want to get the probabilities. So the first sort of symmetry is that the probabilities don't care if they're if they're in sort of energy or time coordinates. Right? So this Gibbs factor equals quotient of times. Another one is that because the constant term doesn't affect energy, we can say the sum of the energies is 0. We're not fixing the internal energy, and we can change this later if we want. Right? We could do sort of an equipartition sort of thing down here, but we won't belabor that. So a little bit of algebra says that if I want to just say what's this beta times E, that we can define that just in terms of the probabilities, and I think that should come as a surprise. And what it means is that as a result, this inverse temperature, if we could form this product here, which we can, we would take this norm divided by that norm, which is just gamma squared plus 1 square root divided by h. That would give us the beta. So if we knew what the norm of h was, we'd be finished. And we're going to get that using symmetry, and then we're going to get beta from that. So how do we get norm of h? So the first thing is some dimensional analysis. So if we have this map that we want from t to h, it's got to depend on some other parameter. And so the Buckingham pi theorem says that the scaling should be of this form. You know, as long as there's just one governing parameter. Maybe you could imagine there's multiple, but we'll be parsimonious and say there's just one. And so let's think about a Hamiltonian system. So you dilate time, and that's what it does to time. It dilates time, and it induces an extended canonical transformation. Space is the same, the momenta are scaled, and the energy is scaled. But this is a change of units, so it can't affect the Gibbs factor. So this term, you know, beta h has to stay the same, and so that implies that beta scales the same way as an overall time scale. And there's other ways you could get the same result. You could look at, you know, a classical gas in a can. You could look at Kubo-Martin-Schwinger, the thermal time hypothesis, which is sort of the same thing. These all give the same sort of result. So we'll work in natural units, and what it means is that, you know, once we've figured out whatever this sort of dependence on probabilities is, we know what beta looks like. So we just got to figure out what the dependence on probabilities is, and we're going to ignore h bar in what follows. Again, natural units. So a little more symmetry. If we have this map t to h as yet undefined, well, we know that the probabilities are invariant under this sort of dilation, right? And we just divide all the times by a constant, the probabilities are the same. And so this implies that this thing gamma is invariant. And so we'll make this ansatz that beta depends on this tuple of times. We make this map, and we carry it through, and this is how h changes. Gamma is the same because p is the same, and so all the change happens in this coefficient out here. And so in particular, the probability vector has to be constant on rays in both sets of coordinates. This is obvious for time. It's not so obvious for energy. So the sort of lemma that comes out of this is that if you have some smooth map that does what we're looking for, and it satisfies Gibbs and this you know, sort of convenient side condition that doesn't actually have physical implications, that it sends sort of pieces of spheres to pieces of spheres. And once we have that in hand, we can get a closed form for everything. So I'll define U to be this sort of vector of all ones that's suitably normalized, so that these two things are, so that this equality holds. And that lemma means that these two norms equal each other, right? It maps portions of spheres to portions of spheres. And if I say, okay, I can actually write down what this is, everything's uniform, so the gammas disappear. Remember, they're all basically, you know, log p minus log p sorts of things. So they all become 0. This is just 1 over beta. And so the norm of this guy is just the temperature. And so we've reduced most of the form of this at this point. We've got this sort of term involving gamma that you've seen before, and this beta of u that we don't know yet. But once we know beta of u, we get everything. Okay, so we've reduced the problem to figuring out what beta of u is. But we already know. We know from scaling, right? It's beta is going to scale like time, and so we just take the norm of t, but that's the norm of p times this t infinity. And we've got some sort of ignorable overall constant. And again, working in natural units says, here's what the inverse temperature is in terms of time coordinates. And again, here's what gamma is when you break it down. And you get a sort of explicit formula if you want to write it out in terms of P and T. So I'll mention that the ideas behind this derivation are mostly due to a former collaborator of mine by the name of David Ford. And, I sort of focused on the scaling argument. And this came out of work done at and by NSA in the late 90s and early 2000s. So you can imagine what people were using it for, and it was subsequently declassified, and they were using it to look at computer network traffic. But we won't dwell on that. So I just want to sort of talk about what this looks like geometrically. I'm showing both sets of coordinates here. On the left, I'm showing the sort of time coordinates, and on the right, I'm showing energy coordinates. And the solid curves here are isotherms. Right, so here's the isotherm for beta equals 1, beta equals a half. Here are the sort of corresponding isotherms. You've got these corresponding pieces of spheres, and I've used the dots to sort of highlight their parameterization and how their parameterization maps back and forth. So you'll notice at the edges there's a big gap between dots here, and the rays get transformed, in the sort of way that I was talking about before. So that's what the mapping that goes the other way in statistical physics looks like. So just to sort of recap what we've done so far, there were just a few symmetries we used, right? So first was an axiom that the 0 point of energy doesn't matter. Another was that the probability of a state only depends on energy. And we used some Hamiltonian mechanics to show that the changing the unit of time leaves that beta h invariant. We could have done that just from a can of gas, but it's a slightly longer argument, more words. And there was this derived sort of geometry that pieces of spheres and rays go to pieces of spheres and rays. So once we have this formula, we say, well, what would we like to use it with? And it turns out to be hard. So if you say, well, this should be sort of intensive, as temperature should be, then, and you sort of carry this through, you look at some product systems, it turns out that this T infinity thing, which I've very much swept under the rug so far, has to be a lot like a mixing time. But it can't be exactly like one, because that makes an example break in its details. So the details of what precisely it should be are a little unclear, but I'll mention in work that's not on the archive that looking at discrete memoryless channels and saying that the sort of free energy of them should try to be extremal, right? That an environment will want to corrupt the communications channel does hint at a solution. So I'm not going to dwell on that, and I'm not going to dwell on what the nature of T infinity would be. If you were going to say, look at an inhomogeneous Markov process, you could take a mixing time and have some success with it, as long as you don't claim that it's the exact answer. If, for instance, you were to look at a single Glauber Ising spin, if you take this T infinity to be inversely proportional to the largest energy scale, then everything sort of works the way that it should. But only asymptotically at the two sort of extremes. So there's some work to be filled in to get things exact with this. But what I'll be talking about for the remainder of my time is if we pretend that the sort of L2 mixing time is a good surrogate for this, as yet unspecified T infinity. and I think there are good physical arguments for that. So as I mentioned, there's sort of obvious applications of this idea to sort of time-varying Markov processes, and what David Ford did in '98, and what I joined up with him on, was to analyze computer network traffic using these ideas. And this came out of NSA and was declassified in 2000 or 2001. There were at least 3 companies formed on the basis of this idea, one of which sold to Cisco for, I want to say, 500 million, and the other 2 later on were not as successful. So, but let's talk about applications to physics. So, like I said, it's hard to find physically relevant examples. So the sort of first thing that you'd want to look at are equilibrium spin systems, like Glaub rising spins. They're Markov processes, and you want to sort of make the ansatz that beta, inverse beta, is the actual temperature, and it implies that this T infinity behaves like the reciprocal of the largest energy scale. It's fine. It's a good sanity check, but it doesn't actually tell you anything new. And in general, why would you look at an equilibrium spin system other than to figure out something about this T infinity, which seems analytically hard, right? You might want to look at a non-equilibrium system like a spin glass, but aging makes that sort of complicated. And you might say, okay, if a spin system is not everything it's cracked up to be, maybe a continuous example. So you need a good phase-space discretization, and both your distribution and the absolute value of its log need to be an L1 intersect L2 to have a nice guarantee that everything is well behaved. And there aren't obvious examples of that. You try to discretize a can of gas, it doesn't really work well because you get UV problems. So, like I said right here, there's problems with UV if you scale a gas. So it turns out that ANOSOF systems actually do fit the bill. And the sort of physical relevance of these things comes from the chaotic hypothesis of Galavati and Cohen. And the gist of it is that you've got some time evolution map T. So that's what's used in the literature. So let's not think of that as temperature. But that's just the time evolution map. And if it's a many particle system, it ought to be mixing ANOSOF. And these maps have natural discretizations called Markup Partitions. And this sort of helps with the fact that the actual physical measure is very singular with respect to phase space volume. Right? The chaotic system lives on an attractor, so the measure is going to be singular. And they have L2 mixing times that are commutable proxies. So we looked at a couple of examples, a cat map on the torus and a free particle on a constant negative curvature surface. And these are general enough that they have a lot of implications. So you could thermostat and sort of weakly couple and argue a lot from here. So I said a lot about ANOSOF systems, and now I'll say what they actually are. An ANOSOF map is, so it's some smooth map, and it's got this sort of hyperbolicity and invariant properties, and you can read as well as I can, but I want to sort of talk about the picture. So the map, or the sort of flow that's an analog of it, takes you forward in time, and there will be some directions of the flow that are unstable and expand. So that's this red stuff here, or pink. And there are some parts that are stable and contract. And if it's a flow versus a map, there's going to be some a neutral direction, which is transverse to to the time evolution. And some of these are mixing and some aren't. The ones we're going to care about are all mixing, and so they're good sort of archetypal physical systems. So as I said, these have nice discretizations. They're called Markup partitions, and the idea is you take these stable and unstable directions, and you use them to form what you'd call a rectangle. So it's generally not a geometrical rectangle, but you just extend the unstable and stable manifolds so that you enclose some part of phase space. And in higher dimensions, these are almost always, well, even for tori, these are always fractal in dimension more than 2. So the picture is highly misleading, except in one of the toy examples, I'm going to show you. So once you've got these rectangles, you say it's Markov if the sort of images cross over each other in exactly the way that you would like. So you take the forward image and it exactly crosses over other rectangles. And you can always construct such things. And these Markup partitions, like I said, will generally be fractal. They'll be quite nasty, but the cases we'll look at will be not so nasty. So the first example that I'm going to talk about is the Arnold cat map. And you take this matrix, you apply it to the unit square, and enforce periodic boundary conditions, or more generally, take any sort of invertible integer matrix that doesn't have unit norm eigenvalues. These rectangles turn out to be parallelograms, sometimes actual rectangles. So in the case of this cat map, they are actual rectangles. And the map itself corresponds to this Hamiltonian, which is not that contrived an example, right? You've got some nice quadratic stuff and this sort of weird little interaction term and this sort of anomalous, coefficient. But it's a reasonable-looking toy Hamiltonian. So the eigenvalues for this map are just the golden ratio to either a positive or negative power, and you get some eigenvectors that just come out of looking at the sort of sine and cosine of some things, and we don't have to remember the formulas because you'll see pictures. But the key is that these eigenvectors have irrational slopes, and so the stable and unstable curves become dense on the torus, and this map becomes mixing. So it's sort of physically reasonable to talk about it as a toy system. So there's lots of Markup partitions for it. I'm showing a few at the top here. What I call RA, RA prime, and RA double prime. So this one has 5 rectangles. This one has, if I recall, 4 rectangles, and this one has 2. And on the leftmost example, I'm showing sort of dotted lines that indicate where there are what I'll call greedy refinements later on. But first I'll talk about sort of more basic notions of refinement. So you take one of these Markov partitions and you push it forward under the time evolution map, and you intersect the images, and you'll get smaller and smaller rectangles. So if you do that for this partition R sub A, this is the result. And so you can see that things get compressed in this sort of stable direction, and they get stretched out in the unstable direction. And these partitions induce probability distributions, right? So if you take the sort of phase-space measure for granted, well, it turns out that the physical measure is the same thing. So that's a sort of nice special case that you don't have singularity here. And once you have this Markov partition, you can just say, let's look at the measures of the rectangles. And you could say, well, let's look at the corresponding effective temperature, right? Now it'll depend on the particulars of the partition, which is not good. So you'd hope for some construction that doesn't depend on that. But insofar as you can say that this effective temperature doesn't depend on the partition via some tricks that we'll go through, the energy will be 2. And if you take these sort of pointwise refinements, it turns out that this quantity, just forget about whatever T infinity is, it's something, that this number converges for these hyperbolic toral automorphisms. And that said, the details sort of depend on your starting point. So if you start with different partitions, you'll get different numbers. And so you might say, well, there's a sign of goodness. Maybe we can take some extremum over partitions. But let's see about the sort of non-triviality of this non-zero limit. So if we were to take a simpler sort of toy example, or putative example, start with the unit interval and just subdivide it repeatedly as if we're doing Bernoulli trials. So, if we take, a coin and do that, just subdivide so that we have 2 to the n things that are the same size, then this limit's 0. Not very interesting. And if we do something that's not 1/2, then that limit's infinity. So, it's hard to get a finite limit, and the fact that we are getting one is sort of interesting already. And like I said, it's very hard to find systems where there is an obvious scaling limit. So these no subsystems seem to be quite special in this regard. And there's some implications that come from this this suggests sort of a particular functional form for what the constant appearing in this inverse temperature is. That, for instance, it ought not to be the square root of the number of states, so that things don't depend on how many states you have. It really shouldn't have that. So like I said, this limit depends on the Markov partition, and the volumes in the parts of phase space vary a lot more as you take more and more refinements. So that's a problem. So the way to get around it is to sort of greedily refine, take partitions that are the most uniform, and I see that I'm running up against time, so I'll try to compress this a bit. So as you do that, this will sort of make things as uniform as they can be, and just say, if you take the sort of most uniform possible refinements, they'll be greedy, and they're generally not unique, but they're close to it. So I'm showing some examples of greedy refinements here. So here is a Markov partition with two elements, the sort of double prime one that you've seen before, just in eigencoordinates. So we start out here, we've got two rectangles of multiplicity 1 and 1, so one of each for the given measures. So here I'm showing the measure divided by the smallest measure in the current partition. So I've got one that's the golden ratio squared, one that's 1. I push it forward, and I get this gets divided here, and I get a new sort of set of measures, push it forward again, and keep pushing it. And you'll notice that these multiplicities stay roughly even. And moreover, the relative measures are more controlled, right? Instead of phi squared in 1, now I have phi in 1. And it'll remain like that. And I can do greedy refinements of these other partitions, and the same sort of control sort of happens. And I won't belabor this. And I'll just say that they stabilize, these measures again. And there's good reason to think that this is more general. And if you wanted, you could say, let's just take the extremum over every Markov partition. And then you could get a unique number for this beta divided by t infinity. So that's maps. Let's look at flows. So you could take this cat map and suspend it and get a flow. That turns out to be not very interesting physically. So what we'll do instead is look at the geodesic flow on a surface of negative curvature. So you've got the free particle Hamiltonian. This is a mixing flow, and it's going to apparently give results that don't depend on the details of geometry. So here's the details. You've got this sort of form for the metric. Geodesics are circular arcs intersecting the circle, and you identify edges according to a sort of pairing that we don't have to dwell on here. And the Hamiltonian, when you write it in the appropriate coordinates, is reasonably nice. So we can actually, using some work by Adler and Weiss, you can actually explicitly form a Markov partition for a map that's isometric to it, and you can push it forward and get refinements, and here's what happens. And you can numerically compute this this thing beta. The mixing time doesn't depend on the genus. It's effectively constant, so we can more or less ignore it. And you can just do this integral to say what is the measure of a rectangle, and do some numerics to help you deal with the size of things. And when you do this, there's a disappointing result, which is when you take these refinements of just iterated push forwards, things diverge. But that shouldn't be that surprising, because these are highly non-uniform discretizations of phase space. So if you do it with greedy refinements, you get the following. You get a limit for this beta it's not zero, it's finite, and it appears that it doesn't depend on the genus. So the mixing time in general is 1/2 for the L2 mixing time. I think that was actually a result of Gallivati. And so we compute beta over T infinity here for lots of different examples of different genus. And so I'm showing genus 2 through 4 here for 10 to the 4th greedy refinements, and I'm units of however many bunches of things there are in a given partition. And so you can see that there's a sort of common limit that, or a limit inferior that starts to emerge. And if I say, look at everything from genus 2 to 40 and overlay those in this inset, you can see that things are laying on top of each other. And so this is a free particle on a surface, and you could imagine getting an ideal gas by taking lots of copies, coupling it, and getting a thermometer. here's a detailed picture of what you just saw, and another detailed picture for lots of different genera. And if you look at the convergence of entropy, you do 1 minus the entropy, it very slowly, extremely slowly, will converge to 0. But it looks like it'll get there eventually. So this sort of culminates in a conjecture for non-equilibrium statistical physics that this beta actually means something. This effective temperature that you can get from data alone and from this sort of mixing or mixing-like statistics really does tell you something about the temperature and energy of systems. And I'll say that any proof seems like it will be extremely complicated because there are lots of technical difficulties involving the different Markov partitions. You've got to do lots of nonlinear estimates for these maps. So it seems like it would be quite hard to get any sort of proofs. So that's what I have. That's where I am at Fast Labs. There's my email, and there are archived links to the papers, and I'm happy to entertain any questions you might have.
Questions?
The beta being half or half of T infinity, this result, do you happen to know if that has anything to do with the so-called page time? So the page time is yeah, sorry, okay. Is there a delay?
I'm sorry, the what time?
The page time.
I'm not sure what that is.
So
I will say that I know it's not like a recurrence time. It can't be, and you can show that. It scales the same way that a topological entropy might. And I guess you're probably talking about a cage time in a spin system now that I think about it, right? In a glass?
No, so the page time is a relation. It's actually a relationship between the temperature of a black hole and the amount of time it takes for the information to leak out of a black hole. Hello?
I really don't know. I've spent a lot of time thinking about what this T infinity should be, and it's still, the details are still very unclear to me. I do feel like there should be a sort of information theoretic characterization of it, and that's why I had started looking at discrete memoryless channels. So the idea that it might be, some sort of characteristic time for information to escape from something seems intuitively plausible to me, and the particular form I couldn't tell you.
I have a question. When you were speaking about the stochastic Lie groups, I came across some examples, but you didn't give the definition. Can you give me a reference to this type of theory and stochastic Lie algebras and so on?
I'm sorry, I'm having a hard time making that out. Can you repeat it in chat or?
Your definition when you introduce the stochastic group. Could you come back to the beginning? Stochastic Lie group. Your definition of stochastic Lie group. Could you hear me?
I'm sorry, I'm having a hard time hearing. If you don't mind, I can call.
Yeah. The question is about your definition of stochastic Lie group.
Okay. Thanks. Okay, so Stochastic group. Okay, there we are. So it's really just everything that has row sums equal to 1. This p times 1 equals 1, that's really just what that encodes. And there are other bases you could have that would be maybe more symmetric. It turns out that they're less convenient to work with, not only here, but if you're trying to do other things like gauge theory, they're not particularly friendly.
Could you give references?
Sure. There's an article by Poole in the Mathematical Monthly from 1990 something, and there's some more recent papers. Let me see if I can actually just dig them up. So let me escape this, and I will try to open. Okay. Okay. So. Okay, so so here's some references: Johnson, Poole, Bucas, Guerra, and Sarychev. And so let's dig those up. So Guerra and Sarychev is here. Johnson is here. Poole is here. So this one, and this one, and I think and this one, which is, I think, the first one that I noticed really looking at the sort of Lie group structure of these. So that might be the most interesting reference. That and the Guerra Sarychev article, I think, also did some Lie group stuff now that I think about it.
Okay. So thank you. Okay. So bye.
Thanks again. Enjoy Mont Blanc.